Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we just talked about the distributed load. If you have the distributed load over the whole beam, then how you can analyze. But most of the times if you see that instead of taking the distributed load, I mean actual distributed load into consideration, we generally take the resultant of the distributed load and we analyze the problem. Okay. But you need to remember that this resultant, when you are taking that, this resultant will be only used to calculate the support reactions and other forces. Okay. It cannot be used, okay. The resultant force cannot be used or the concept of resultant force cannot be used to get the shear force and bending moment. Okay. The internal forces and moments cannot be obtained by considering the resultant force only. Okay. So, we need to know that if you have the distributed load, then how conveniently you can convert that thing to the resultant force and how you can find out the support reactions. Okay. Now, let us talk about that. Suppose if you have this kind of say distributed load, okay, RA. So, over the beam where RA and RB are the support reactions, this is your say x direction, this point is B, this point is A, and you have the distributed load like that. Okay. And you are considering one small element dx, okay, and this total load is say q dx, where q is your uniformly distributed load intensity. So, this is your say y direction and this distance say x and the total length of the beam say L. Okay. And q is the load intensity. And if I consider the whole distribution, the resultant of the whole distribution or the whole distribution of load is nothing but say R, which is acting say x distance, x bar distance away from say y axis. Now, what is my objective? My objective, or what I am saying, that instead of considering the concept of the distributed load, that the way we have solved last problem, if you recall, okay, triangular distribution load and all, there we considered a small element and we considered the load intensity multiplied by the small length, and that will be nothing but a concentrated force, and that will be integrated over the whole length. We did like that, right. So, instead of doing that much of complicated thing, I can simply consider this resultant R means resultant of this whole distribution, okay, and the distance of this resultant from the y axis, which is nothing but x bar. If we can calculate these two things, that will be well enough to find out the support reactions RA and RB, instead of taking or instead of considering the distributed load. Okay. Let us do that. Now, considering the equilibrium, if you consider the equilibrium, okay, that means summation of Fy equal to 0, I can simply write Ra plus Rb minus 0 to L q dx. So, equation 1, and that is from your distributed load consideration. Agreed or not? So, that is coming from distributed load consideration. So, whatever we did earlier, whatever we learned so far, okay, when you have the distributed load, we are not talking about the resultant or all those things. So, if you consider the distributed load, that is Q dx is the concentrated force on the infinitesimally small say length dx, okay, and I am integrating over 0 to L, that is giving me the total load, and based on that I can consider this is my equilibrium condition. Of course, this is 0, so fine. Okay. Now, if I consider only the resultant force, then I can simply write R A plus R B minus R equal to 0. So, that is from resultant force consideration. Okay. So, from equation 1 and 2, what I can write? R A plus R B minus 0 to L Q dx is equal to R A plus R B minus R, because both must give me the same effect. As I told you, the main thing is that what we are replacing the distributed load, the complicated thing, okay, by the resultant force of the distributed load R. So, in this process, this equation, if I say this equation is satisfying my equilibrium condition, and this equation is also satisfying the equilibrium condition from the resultant force consideration, then they must be same. If they are same, then I can simply write R is nothing but Q dx. Okay. So, your resultant force is nothing but this, and now based on that, once you get the resultant force, you just put it in this equation, you will be getting the expression for R A and R B. Okay. Fine. Now taking the moment equilibrium. Now, if you take the moment equilibrium, say suppose M A, moment with respect to a point is 0, okay, summation of moments, all moments. Now, what I can write? R B into L, okay, minus 0 to L x into Q dx equal to 0. So, that is equation 3 from distributed load consideration. If you consider the distributed load, so this is the equation coming from the moment equilibrium condition. Okay. So, if you consider the resultant force, then what we will be getting? R B into L minus R into x bar, that is 0. So, equation 4. Okay. So, that is coming from resultant force consideration. Agreed? And they must be same again by following the same logic whatever we did earlier. Okay. So, they must be same. So, therefore, I can simply get R x bar is equal to 0 to L x Q dx. Okay. So, from there I can simply write, x bar equal to 0 to L Qx dx by R. Okay. Therefore, what we can comment, whatever we have got just now, the resultant is equal to total area of the loading diagram, right. R, what is the expression for R? Resultant force R is equal to 0 to L Q dx. So, therefore, the resultant is equal to the total area of the loading diagram, fine. And the second conclusion what we can draw from this, the line of action of resultant passes through the centroid of the loading diagram, that you are getting from here, right. The line of action of the resultant passes through the centroid of the loading diagram. So, this R will be always passing through the centroid of the loading diagram. Okay. So, these two statements or these two conclusions we can draw from this analysis. Now, one thing you will appreciate, that this resultant or the concept of this resultant is valid only when you are talking about the, or you are trying to find out the reactions, external reactions. Now, what I mean to say, suppose this is my beam, okay, simply supported some beam RA, RB, and you have the say distributed, uniformly distributed load with load intensity Q, say. Okay. Now, to find out RA and RB, this resultant business will be fine enough. Okay. That means, if you want to find out RA and RB, so in this case both RA and RB will be same, and so RA equal to RB equal to the area under this loading diagram. But if you want to find out the bending moment and shear force, then suppose you are taking one section here, section 1 say, okay, and you know the resultant of this loading diagram, the whole resultant of this whole loading diagram, say R, which is passing through the centroid of this loading diagram, that comes from the second statement. Now, if you try to find out the shear force and bending moment, okay, under this kind of distributed load, that is not exactly same if you consider this kind of thing. They are not same. What I mean that these two things are not same as long as you are trying to find out the bending moment and shear force. So, therefore, this concept of resultant and the line of action of the resultant force will not work when you are going to find out the bending moment and shear force in a particular section. Okay. So, there actually you can again you can consider that thing by considering the resultant and the line of action of the resultant for this much of loading. Here actually you have to modify. So, you cannot consider the global resultant and the line of action of the global resultant into the consideration of your bending moment and shear force calculation. Understood? Okay. So, these two things are not same as long as we are going to find out the internal forces and moments, that is nothing but shear force and bending moment. Okay. So, now we will try to establish the differential equilibrium relation. Okay. Now, let us see how we can establish that. So, differential equilibrium relations. Okay. So, suppose this is my beam. Okay. So, this is the say x direction, this is say y direction. I have some distributed load over the beam. Okay. That is nothing but say intensity is say qx. I am considering one small segment on the beam dx at x distance away from the origin. Okay. And I am trying to blow it up, okay, this small segment, and I try to draw the free body diagram of this small segment. Okay. So, if I try to draw the free body diagram of this small segment dx, this is some exaggerated figure. Okay. You have load intensity on top of that is qx. Okay. So, this is yx and this is your dx. Okay. This is the midpoint of the segment say O. So, therefore, on this side you will be having the shear force V and all are positive MB. On this side you will be having some variation in the shear force, that is V plus dV due to the travel along the distance dx, and you will be having MB plus dMB. Okay. So, now this thing again I can draw in terms of my resultant concept, whatever we have just learned. This is midpoint O, this is dx, x distance away. Okay. And this resultant say R is approximately can be written as q into dx, fine enough, and all the forces will be remaining same, V, MB, V plus dV, MB plus dMB. Okay. So, this R, as per our definition of the resultant force, R should pass through the midpoint of this element through O. Okay. So, now if I apply the equilibrium condition, say Fy is 0 for this element, small element, I can simply write V plus dV, okay, minus V minus q dx equal to 0. Agreed or not? Fine. Okay. So, from this I can simply write dV dx equal to q. This is the differential relation between the shear force and your load intensity q. Okay. Similarly, I can consider, or from here we can write, say V is nothing but the integration of q dx over the whole length, that is my shear force, that also I can write. Okay. I can consider the moment equilibrium as well. If I consider the moment equilibrium, moment with respect to midpoint O, then I can write mb plus dmb plus v plus dv into dx by 2 plus v into dx by 2 minus mb. Okay, equal to 0. So, from there I can write dmb plus v dx plus dv dx. So, this term is very small, so therefore, we can neglect. Okay. So, from this I can simply write dmb dx equal to minus v. This is another important differential relationship, differential equilibrium relationship. That means, so that is why you might have seen when I was talking about the bending moment is always one order higher than the shear force, right. At the time I was just giving the hints of this relation. So, that means if you do, or if you take the differentiation of the bending moment, right, you will be getting the shear force. Or in the other way, you can simply get mb x is v dx, but opposite in sign. So, that depends on the loading. If you consider the loading in the vertical downward direction, that will be like that. So, what I mean to say, the shear force will be always one order lower than the bending moment, and the differentiation, if you have the equation of the bending moment, okay, you differentiate that equation, you will be getting the shear force. Okay. So, with this I will stop here today, and this is the chapter for your bending moment and shear force calculation for the slender member. Then in the next lecture we will be taking couple of numerical problems, okay, and that will conclude this chapter, and then we will move to the torsion or the twisting moment, okay, for the circular shaft. So, thank you very much.